Hello, I'm Andrea Woodward of the USGS Forest and Rangeland Ecosystem Science Center, and today I'm going to present a tutorial demonstrating the use of a system dynamics model of fish populations, a model that Alicia Torregrosa, Marianne Mayday, and I developed for the San Francisco Bay Area network of national parks. This example model is for Olema Creek, a watershed in Reyes National Seashore. The overarching purpose of this project is to develop methods to integrate among vital signs monitoring datasets for the National Park Service. Working among these datasets can be challenging for a number of reasons, including short duration, measurements not corresponding in time or place, methods and quality checks varying through time, missing data, and the need to incorporate expert knowledge when data on important factors were not collected. We found that system dynamics modeling can be an effective means to meet these challenges. And to illustrate the point, this tutorial demonstrates the use of a system dynamics model and the example of salmon population dynamics. We built the model in Stella software, but other software packages are available. The goal of the presentation is to give you tools to interact with the model rather than provide a comprehensive demonstration of the features of Stella. A free, limited capability version of the Stella software, the model, and the input file can be downloaded from this website. Let's start with background on the life cycle of coho salmon. What is of interest to the park is the freshwater stage of the life cycle, because that is what occurs in their jurisdiction. What happens is that spawners return to the watershed in December to February. They build redds, lay eggs, which hatch into alevins and emerge as fry in the spring. Then the juveniles grow in the freshwater habitat through the summer, fall, and following winter until they smolt in the spring and return to the ocean. After 18 months in the ocean, they return to freshwater as spawners and repeat the cycle. But as I mentioned, it is the freshwater stage of the life cycle that is of most interest to the park. So to model the freshwater stage of the life cycle, we used a system dynamics modeling framework, which consists of stocks, which are things you can count, and flows, which describe the change in those stocks over time. Then we can also incorporate converters, which are factors that affect the rate of flow in any given time period. For example, a couple of stocks might be eggs that become juveniles through the flow of survival. And an example of a factor that might affect the rate of survival is high stream flow events. For the Olema model, we looked at it in a slightly more complicated way. We found it easier to describe the factors affecting fish by looking at how those factors increase mortality rather than how they decrease survival. So we modeled survival as what is left over after the mortality factors have reduced the stocks. These cloud symbols represent stocks we are no longer keeping track of. So once the eggs have died, they are gone from the model. Looking at the Olema model more completely, it consists of four main stocks: eggs, juveniles at the beginning of summer, juveniles at the end of summer, and smolts, with survival occurring between each pair of stocks and mortality diminishing each stock. The model runs on a weekly time step, and for each section of the model, there are mortality factors and inputs. In the first part of the model, eggs to juveniles at the beginning of summer, we have baseline mortality, which accounts for all of the mortality that we are not specifically keeping track of, scouring stream flow events, which are those stream flows that disrupt the redds, and what we are calling fry stress stream flow events, which are stream flows that are high enough that the fry are forced to put all of their energy into swimming against the flow to avoid being washed out, rather than being able to feed. The inputs to this part of the model are eggs and weekly high stream flow levels. During the juvenile phase of the model, juveniles beginning of summer to juveniles end of summer, we once again have baseline mortality, a juvenile density effect, which accounts for competition among fish, Summer low flow, which can decrease dissolved oxygen and or increase the vulnerability of fish to predation, and high stream temperature. Inputs are weekly low flow values and weekly average air temperature, which is a surrogate for water temperature. In the winter, second spring part of the model, between juveniles end of summer until they become smolts, we once again have a baseline mortality factor, a density effect, as well as high stream flow and poor habitat. The inputs to this phase of the model are weekly high stream flow and a habitat index. Now let's go to the model itself. So we'll switch to the Stella software. First, let me orient you to the display. Notice that up the side of the screen we have some tabs. At the top we have the interface view. I'll come back to this in more detail, but this is a place where you can run the model and also easily experiment with it by changing the parameters between each run using these slider bars. Next we have the Map tab, which shows a simplified diagram of the model. You can see the same elements that I was describing earlier. Boxes for stocks, arrows with valves for flows, circles for converters, and clouds for stocks that disappear from the model. You can see the same four stocks that I described earlier in the boxes across the top. Eggs, juveniles at the beginning of summer, juveniles at the end of summer, and smolts. You can also see the survival flows, the mortality flows, and the rest of this just implements all of the factors that I talked about. We have a few additional stocks down here that are basically counters of stream flow events. Next is the Model tab, which describes the nuts and bolts of the model in more detail. We'll come back here shortly. Finally, under the Equation tab, you can look at all of the equations that run the model. Let's go back to the Model tab. If we look inside some of these converters, for example, Fry flow event threshold, you can see that we have a number, 200. And if you click on the Documentation tab, you can see the documentation that explains the units that the number represents and the source of the number. So you can see that this number was chosen based on expert knowledge. Now let's look at mortality due to scour events. Once again, you see there is a number. And if you look in the documentation, you can see that this number was based on data and a description of how it was derived. Now let's look at mortality due to stream temperature. This time we have an equation. What we have done here is to predict stream temperature from air temperature, because the data record for stream temperature is much shorter than the record for air temperature. So here, average weekly stream temperature is a function of average weekly air temperature. This equation says that if the predicted stream temperature is greater than a stream temperature threshold thought to be detrimental to fish, then apply the fish mortality factor, else do not apply anything. So you can see that there can be all sorts of things inside of the converters, primarily numbers from various sources and equations. Also note that we have these little symbols on the converters. They each represent a slider on the interface, so they each provide an opportunity to change the numbers every time you run the model. I'm going to talk more about this later. Also, some of the converters have graph symbols. This just indicates that they contain graphical data. Now, before we run the model, let me show you the input to the model, which is in an Excel spreadsheet and looks like this. In this spreadsheet, we have a tab for every year for which we have data. And each tab has an initial eggs value, the week during which spawning began, the week when the last red was observed to be built, a habitat value, which is basically an index describing habitat quality, and environmental variables. So we have the weeks of the model down this side, and I've highlighted in blue the weeks between the beginning of December and the end of May, which represent the first section of the model. And for this section, we have values for spring ice stream flow on a weekly basis. In the next section of the model, we have summer, weeks 27 to 46, with summer low stream flow and average air temperature. And then from the middle of October to the end of March, in the last part of the model, we have high stream flow again. The purple signifies that these are estimated values, which we had to determine from other sources because they were missing from the values in the Olema Creek data set. Now back to the model. You can run the model from several tabs, but let's use the Interface tab. In order to run the model, we must first import the data I just showed you. Go to the Edit tab, click on Import Data. I recommend that you do this just one time rather than establishing persistent links. You browse to the place where you have the input file. Open it, and then choose the year by using the drop-down menu next to worksheet name. Here you can see all of the years that we have data for. We'll just use the first one. Be sure that the data orientation is this, where you have the headings across the top and values down the columns. Click OK. You get a dialog box telling you that the data have been successfully imported, and then you can run the model. Click OK. Go to the Run tab and hit Run. And then you can watch the model run. Now let's look at the table. This table begins at the beginning of the time steps and runs through all the weeks of the model. You can see that all of the mortality from the first part of the model is applied in one step at week 26. So beginning with nearly 52,000 eggs, you end up with about 12,000 juveniles at the beginning of summer. That number declines until the end of summer, and then the remaining fish are transferred to the next stock. Then the final mortality is applied at the end of the run. So you end up with about 3,300 smolts. If you want to include other values in the table, double-click on the table and add any variable that you want. And if you want to remove a variable, just do the reverse. If we look at the graph, we can see that it is set up with the same values that are in the table. Notice that each has its own scale. So eggs are on a scale from 0 to 60,000, while juveniles beginning of summer are on a scale of 0 to 20,000. This is done so that you can actually see the relatively small numbers towards the end of the run. The scale automatically adjusts for each model run. If you want to modify the graph, double-click on the graph. Then you can use the same steps to add and remove variables as you did on the tables. You can also change the scales and make other modifications, but I'm not going to go into these features. Next, you can run through all of the years in the same way, or you can use the interface to play with the values and see how changes in some of the parameters might affect the outcome of the model. One way to do this is to simply take base mortality factor spring, for example. Let's say you want to see what happens if base mortality spring is higher because you suspect there's disease in the system. Change the value and rerun the model. Once you've done that, if you want to go back to the default value, click U or Undo. Also in this view, if you click on the question mark, you'll see that you have access to all of the documentation that was available in the model view. Also, if you want to change any of the graphical input data, for example, the flow regime for any model run, to perhaps simulate the effects of climate change, you can go into this graph by double-clicking on it. Then you can simply click above or below the original line to modify the flow regime, and then rerun the model. I also want to show you the SensiSpecs feature, which allows you to do a sensitivity analysis. So we'll look at that in more detail. You go to the Run tab, click on SensiSpecs, and pick a value for which you want to look at the sensitivity of the model. Let's take base mortality winter spring 2 and make that the selected value. Highlight it, and then enter the desired number of runs. We'll stay with 3. Pick a beginning and ending number. Let's use 0.1 and 0.3 to bracket our default value of 0.2. Click on Set. It will distribute those values evenly over the number of runs that you requested because incremental is selected. Sensitivity is now on. Click OK. Now let's go to the graph and set it up to display the results. Double-click on the graph. We want a comparative graph. Probably the most interesting number is the number of smolts, so we'll make that the selected value. Because smolts appear at the end of the model run, we'll just run the last few steps of the model. We'll stay on page 1 of the graph and click OK. Now let's set up the table. Double-click on the table. Again, let's look at smolts. We want a comparative table. We stay on page 1 and click OK. Now we'll run the model. Go to the Run tab. This time you see an S in front of Run, indicating that you're running SensiSpecs, and run the model. You will see 3 model runs. Now you have a graphical representation of the differences among the runs, and you can also look at the table to easily see the actual values. Now you have a sense of how sensitive the model is to changes in base mortality winter spring 2. To clear the graphs and tables, click the dynamite symbol. Please remember that each year of data has different numbers of eggs and environmental conditions, so sensitivity to various factors will vary with year. So, with this tutorial, I've tried to give you enough tools to experiment with the model we've developed, and we hope you find it interesting to do so. In conclusion, I would like to thank the San Francisco Bay Area Network, and especially Michael Reichmuth and Darren Fong, for helping design the model and populate the relationships. Not only did they and others provide data for this analysis, they also provided expert knowledge and great discussions. We would also like to thank the USGS Status and Trends and Land Change Science programs for funding us to explore ways to synthesize vital signs data. Finally, the full documentation of the model, including a detailed description and rationale, can be found at this website. Thank you.